So let's go ahead and get started. My name is Dr. Wu. I see a lot of familiar faces from my class last semester. So it's good to see you guys again. So this is just going to be an introduction of myself. So I graduated from Texas A&M twice, once in 2006 with a BS in physics, and then I graduated with my PhD in August. I'm going to be making videos this semester, so you can see we're actually recording this lecture right now. So I'm making videos both as the pre-lecture videos, so they're going to be general videos on equations and concepts that you can watch before class. And I'm also going to be making videos of our class so that you can see the problems that I solve again. If you are having difficulty, you didn't follow something that I did the first time, or you'd like to review that. This is the second semester I've been teaching at UC. My personal interests in physics are in particle physics, general relativity, cosmology, and physics education. And just a fun fact about myself, I'm a citizen of Switzerland, actually dual citizen, so I'm a US citizen and citizen of Switzerland. And I played ice hockey for probably close to 25 years now. Okay, so now I'd like to introduce the team, so if you'd like to go first.
Hi guys, my name is Zamar. I am a third-year physics and astrophysics student, and I'll be you guys' SI leader. So hopefully you guys know what SI is, but if you guys don't, basically what we do is hold sessions outside the classroom. It's not another lecture. What we do is collaborative work study, so you guys work in groups, and I'll present all different kinds of problems that you guys will see somewhat on the exam or on your homework, so hopefully it'll give you guys a good idea on how you approach these problems. And so my sessions are every Tuesdays and Thursdays, and they're right after class. It goes from 4 to 5:30 at Bronstein 325, and that's my email address if you guys have any questions. First session starts Thursday, so if you have any other questions, just email me or ask me after class.
Okay, you want to just give yours from back there?
Yeah, that's fine. So my name is John Thompson. I'm a 7th-year graduate student here at UC in physics. I primarily do work in condensed matter physics, and more particularly optics. I'm an experimentalist also. I'll mention something briefly about the Learning Center. It's in the Geology Physics building. It's room 304, I believe, 304, 303. Those typical hours are between 9 and 5, Mondays through Fridays. Each TA will be assigned to, not just me, there's several other TAs teaching other things now. We all get assigned to Learning Center hours. I don't know my hours yet, I'm still deciding it. Well, my point of the matter is, you can kind of go in there any time that there's a TA in there. It doesn't have to be me. So if my hours don't work for you, that's okay. There's usually a TA in there anyway, like I said, between 9 and 5, Mondays through Fridays. So you can go in there anytime you have problems with physics, homework, it can even be lab related and things of that nature too. There's actually another TA that's supposed to be here right now, Shovik. Unfortunately, he's sick at the moment, but just so you know, there will be another TA also.
Okay, great, thanks. So now that we've introduced ourselves, take a moment to introduce yourself to each other. So we're going to be collaborating a lot. So just out of curiosity, does anybody know what this question right here has to do with? Is anybody watching AGDQ? Nobody? There was somebody this morning watching it. So what AGDQ is, it's Awesome Games Done Quick. It's a charity event that's going on all this week, 24 hours, to raise money for the Prevent Cancer Foundation. So what it is it's a series of people playing video games as fast as they can to be able to raise money for charity. Right now, I think it's a Metroid block right now. I think Metroid Prime 3 is going on right now. Might sound like I'm speaking Klingon to some of you, I guess, but okay. So why are we here and what can we get out of it? So this class is really, there's some core concepts that you should take away just for general citizenship, things that you should understand about physics. But really what we'd like you to be able to do by the end of this course is to be able to think like a scientist. You should be able to develop critical thinking skills over the course of the semester. In doing that, you'll be able to appreciate the world in a deeper way. also with this first point, there's a video that goes with this. There are other reasons that you should take this class. The LSAT is the exam that you might take if you want to go to law school. There is a logic game section of that test, and people that take physics tend to do much better on that exam. The MCAT also has a physics portion of it, so in preparing for that test, taking this class is a good idea. And who knows, we could possibly, maybe even have a little bit of fun. Okay, so to motivate the point about thinking like a scientist and what that can do for your career, here's a portion of a commencement speech given by Neil deGrasse Tyson.
If you're an employer and two candidates come up looking for a job, and this is, again, a contrived example, and you're interviewing the two candidates, and you say, and for part of this interview, I just want to ask you, what's the height of the spire on this building that we're in? And the candidate says, oh, I was an architect. I majored in architecture for a while, and I memorized the heights of all the buildings on campus. I know. The height of that spire is 150 feet. In fact, 155 feet tall. Okay, turns out that's the right answer. That's the right answer. The person came up with it in seconds. That person goes away, the next candidate walks in. Do you know the height of the spire on this building? The candidate says, no, but I'll be right back. Person runs outside, measures the length of the shadow of that spire on the ground, measures the length of her own shadow, ratios the height to the shadows, comes up with a number. Runs back inside, it's about 150 feet. Who are you going to hire? I'm hiring the person who figured it out, even though it took that person longer, even though the person's answer is not as precise. I'm hiring that person, because that person knows how to use the mind in a way not previously engaged. You realize when you know how to think, it empowers you far beyond those who know only what to think. Heck, I should tweet that. It's a tweetable thought. Just hang on a second. I'm going to tweet that. Forgive me. I beg forgiveness here. Actually, I don't beg forgiveness. I demand it.
Okay, so I think that Neil deGrasse Tyson makes a really good point here in that when you are looking for a job, you want to be able to demonstrate to people that you're not just a person that's loaded with a bunch of facts that can spit out, random factoids. You want to be a person that knows how to generate new knowledge and be able to think critically. And that's something that we hope to help you develop over the course of the semester. So in order to do well in this course, or what are the things that we need to be able to do? So before class, you should watch the videos posted on Course Networking and take notes on them. And like I said, I'll be posting some of my own videos in addition to the videos that Dr. Marius is going to be posting. You want to read the textbook. Now, I put an asterisk here because I'm going to come back to that point. You should be reading it in a very particular way. You should be completing the assignments that we give you, both the pre-lecture assignments and the homework assignments. And in class, we'll do a short review of the material. We'll have learning catalytics problems, and we'll have other activities, videos, and demos, and the like. So to come back to that point about reading, here's a graph that compares two different methods of study. One, somebody studies a bunch and then they study again. That's the study. And then another one, somebody studies and then assesses how well they absorbed the material that they studied. And then they can revisit studying again. And what the research finds is that just reading and not testing yourself doesn't really improve your retention very well. So you can see this drops off very quickly. Whereas if you read and then you assess yourself and say, how well did I actually learn this? You tend to keep that information more. So in doing the reading and watching the videos, it's good to start there, but then what you should be doing is when you take the homework assignments or the pre-lectures, you should be thinking about, how well do I know this really as I'm doing this? I got the answer wrong. What is it that I need to look up again to make sure that I know the material as well as I should? Okay, so this is just a breakdown of the grades. They're going to be the same as they were last semester. So each of the 3 exams were 12%. The final exam is 24%. The in-class activities count for 24% as well. So when you think about it, in the grand scheme of things, the final exam is exactly the same as coming to class every day and doing all of the activities. Homework is 16%, and you can earn an additional 2% bonus by interacting with each other on course networking. So last semester we used course networking, but I want to clarify how it's going to be a little bit different this semester. So last semester we didn't give you guys a lot of guidelines for how we wanted you to use it, and as many of you know, that kind of just turned into a seed race, and people setting up scripts to watch videos 100 times, or just posting polls about their dogs or something. So we wrote into the syllabus that we really want you guys to use course networking to watch the videos and to post questions that you have and respond to questions that other students have. And if we find that there's activity that we don't want going on there, we're going to take it down. Okay, and if somebody creates enough of a disruption, we may even remove you from course networking, which forfeits your 2% here. So it's not really meant as a threat, but really just to get you to think that there's a reason why we're doing this, and we want you to follow those guidelines to get the most out of it that you really can. Okay, so let's start into the actual physics. So this class is based on E&M, and so with E&M we start with charges. So consider 2 pieces of tape that are stuck to a table, and each piece is ripped off quickly. Afterwards you bring them close to one another, and they seem to repel each other. Why does this happen? Go ahead and talk to each other and try to figure out why this is. All right, so let's come back together and talk about this one. So how about somebody like right around here? What do you guys think? What'd you come up with? What's that?
They have the same charge.
Why? It's a good guess, right? Because we know that they repel each other, right? What do we know about the way that electric charges behave? So say I have like charges, are they going to attract or repel? Repel. And if I had different charges, they're going to attract, right? So because we know that these are repelled, we know that they have to have the same charges, right? So the question then is, how are they getting the same charges? You guys have any ideas here? Yeah?
There was transfer of electrons when they were stuck on the table.
Right. So why is it a transfer of electrons, not a transfer of protons?
Because electrons are found on the outer shell and
Right.
are easily lost, and the protons are in the nucleus of the atom.
Right, very good. So we know from our understanding of atoms and the simplified kind of solar system model where the electrons go around the nucleus, that you have a positively charged center that is protons and neutrons, and you have electrons on the outside, right? And so when I ask which one is it that you pull off, you're pulling off the electrons because they're on the outside. It would be very difficult to reach all the way into the atom and pull out the nucleus. In fact, I mean, it's impossible to do that and have the electrons stay where they are. Okay, good. So let's do another one. Talk to each other about this one. What's going to happen if we had these 2 together, 2 pieces of tape together, and then we rip them apart? Good. Okay, sounds like you guys are pretty good at this, so let's talk about this one. Would anybody like to offer a hypothesis about what's going to happen here? Or care to explain why they're attracted to each other? Yeah?
So when you rip off one side, whichever side takes the more electrons, it makes that side more negative, but then the side that got the electrons ripped off becomes more positive because of that, which creates the opposite attractions, making them come back together.
Right, perfect. So we had these two together, and they're neutral to start out with, and when we rip them apart, the electrons are removed from one, so one of them gets a net negative charge, and because the electrons are not on the other one anymore, that one's left with a net positive charge. Very good. Okay, now I can't read this from the angle I'm at. So in the first example, when the two pieces of tape were ripped from the table, okay, quickly, talk about it. The electrons, right? I already answered my own question already. We know that they're the electrons because the electrons are what's on the outside of the atoms. Okay, good. Okay, so here's a pretty cool demonstration here. Kind of chill music too. Okay, so what did we do to that pipe? We charged it, right? So that pipe has a charge now. The metal can is electrically neutral. And so we were talking about before, we know that opposites attract, right? And we saw very clearly that this charged pipe was attracting a neutral can. So talk to each other and try to figure out why that is. Okay, so let's go ahead and talk about this one. So when we're looking at our can, we say that the can is electrically neutral, but that doesn't mean that it doesn't have any charge in it at all. It just means that the positive charges are exactly balancing the negative charges. And so these are all kind of scattered throughout like this. So they come in pairs, but they're scattered all over the place. Now, something special is going to happen when we bring a negatively charged object near this, because of the type of material this is. What type of material is the can?
Metal.
It's a metal, right? What's special about metals?
Conductor.
It's a conductor, which means?
The electrons are delocalized.
Yeah, the electrons can move around, right? So when I bring this negative pipe next to the can, the electrons over here are like, well, we don't like electrons. We're going to move away from them. So what they do is they all move over here, which means that there's a deficiency of electrons, and when there's a deficiency of electrons, that's a net positive charge. So by bringing this close to the can, it polarizes it so that this side has positive charge and this side has negative charge. And that's why the can is attracted to the pipe. Okay? Any questions? Yeah?
When I thought we just discussed the fact that if you have similar charges, then they repel. So if you move all the negative charges on one side,
good. So this is, it's kind of a matter of what situation can give you the lowest energy, right? And so you're absolutely right. If this wasn't here, it's going to move back to the way that it was. But these electrons dislike having this over here so much, they'll try to move away. Even though without this, it would never be in that state. Okay, does that make more sense? Okay, any other questions? Okay, so let's move on to the next one. So if I rub a plastic ruler in my hair and bring it close to a small piece of paper, both the ruler and the paper are insulators. What's going to happen? Go ahead and discuss. Okay, so let's talk about this one. This one's a little bit harder. Some of you know the answer because you've seen it done before, but the real key is to be able to explain why it happens. So what is the answer? B, right? It's going to be attracted. Why? Anybody care to offer The reason why, yeah.
Is it because even though the paper is neutral, the ruler is still more negative, so there's an attraction factor between them?
Not quite. That is important though. It's important that this is negative because that's going to cause something else to happen in the paper. So we know there's some rules that we can play with to solve this puzzle, right? We knew from the last one that with the metal, the electrons were allowed to move around, right? If this was metal and I brought a negative charge here, all of these electrons just move to the other side. Well, because this is an insulator, that's not allowed to happen. But something else might be allowed to happen that gives this favorable orientation for this to be attracted. Yeah?
The electron, their density moves to the other side of the nucleus they're on?
Right. So these atoms, they're fixed in place. So they can't, this electron can't leave its nucleus, but what it can do is it can rotate. And this is going to rotate so that the negative part is going to be far away. This one's already over there. Right? Does that make sense why this is going to be attracted? Because the positive parts are always closer to this than the negative parts. All right? Any questions? Okay, let's move on to another one. Actually, this is a quick video. And this works on the same principle. This is what's going to happen if you have running water and you bring something that's charged close to it.
And I'm Steve.
And this is a piece of PVC pipe.
And this is a plastic cup that has a hole drilled into the bottom of it. So when I fill it with water, it leaks out of the bottom.
If I charge the pipe and then bring it close to the stream of water, the water is attracted to it. That's because water molecules are polar molecules.
Water molecules look a little bit like Mickey Mouse. The two hydrogen atoms are bunched up on one side of the oxygen atom. And while the molecule itself is neutral overall, it has a positive end and a negative end because of the way it's shaped. Molecules like water that have an asymmetrical distribution of charge are called polar molecules.
Let's say the pipe has negative electrical charge. If I bring it close to the stream of water, the water molecule flips so that the positive end is pointed towards the negatively charged pipe. Opposite charges attract, so the water is drawn towards.
So when the water's falling down like this before they bring the charge close to it, it's all randomly oriented like this was before, right? And then when they bring the charge close, the water molecules are pulled towards the charge.
A cone.
Or a balloon that you've rubbed on your head.
Yeah, these guys are kind of goobers.
Plastic pen.
All right, there's like another 30 minutes of them testing random things. Okay. All right. So this one requires a little bit of introduction. A pith ball is just a very light styrofoam ball. Okay. So you take a small pith ball hanging by a string, and you bring a negatively charged rod next to it, and slowly move it towards the ball. And then you touch the ball and the rod together. What's going to happen? Go ahead and discuss. Okay, so let's go ahead and talk about this one. So, what did we think? How about for the first part anyway? Before the contact? Attracted. Why? You guys should get used to me saying this. I don't just want an answer, I want a reason.
The reason, we talked about before of negative, the rod is negatively charged and the positive charge, not the positive charge, but the positive protons of the pith ball will attract the negative.
Right. So it's exactly like the paper that we had before. We had something that was neutral and we bring something negative towards it, and these charges, these atoms are going to orient themselves in a way that they're going to attract each other. Okay, good. So somebody else, who thinks they know what's going to happen afterwards? What's going to happen? Yeah. Why?
because the rod is charged, so some of that negative charge is going to jump to the ball.
Good, good. So we had our charged ball, or sorry, our charged rod and our neutral ball. And remember, charge always wants to be in a lowest energy state. It's lazy. It doesn't want to have to do a lot of stuff to hang out, right? It just wants to, you know, lounge around, I guess. So what that means is it doesn't like being near other charges, and it's going to do everything it can to be away from other charges. So when you touch them, some of that negative charge is going to jump over, which means that both of them are net negative now, and they're going to repel each other. Good. Okay. So this one takes a little bit of a setup to explain too. A electroscope is a metal ball or metal wire that has two little leads that come off at the bottom here. And these leads are allowed to move around. Okay, so consider what's going to happen when I bring this negatively charged bar near this metal electroscope. Go ahead and talk to each other about it. Okay, so let's talk about this one. So tell me, for this arrangement, what do we know about the electroscope? What material is it made out of? Now it's kind of a gimme, right? Because it's written on the slide, right? What kind of material is the electroscope made out of? Metal. What's allowed to happen in metals? Electrons can flow, right? So when I bring this negatively charged rod close to the top of this, where are the electrons going to go? Into the legs. Into the legs, right? All the way at the bottom. They're going to want to come in equal proportions into this and this, right? So when that happens, what's going to happen next? So somebody new, over here. What do you think?
Those are going to move away from one another?
Yes, because these are negatively charged, negatives repel each other, and so they're going to move away. Good. Okay, so here's a short video of some electroscopes.
Hi folks, I'm going to show you how to inductively charge an electroscope, but in such a way that even when you move the charge object away from the electroscope's terminal, the foils or leaves will still repel each other. You probably already know that if you hold a charged object like this negatively charged piece of vinyl near the terminal of an electroscope, the foils or leaves will repel each other. They move apart, like this. And when you move the charged object away, the foils no longer repel each other. They move back together, like this. But to make them repel each other after you move the charged object away, there's just one small step you have to add. Before going into detail of why it works, here's a quick demonstration. All it takes is your finger at the right time and the right place. The key to understanding this is to understand that normally the number of positive and negative charges on the electroscope are equal, and they stay equal. If there's no charged object around, then they're also balanced out everywhere. Wherever there's a positive charge, there's a negative charge to balance it out, or neutralize it. When we move a negatively charged object near the electroscope's terminal, all we're doing is forcing the negative charges away from the terminal and down to the foils. And they'll stay there as long as the charged object is around. When we move the charged object away, the negative charges return to where they were and everything's balanced out or neutral again. Everywhere that there's a positive charge, there's a negative charge to neutralize it. But now let's see what happens if I touch the terminal with my finger while the charged object is near the terminal. We start with an equal number of positive and negative charges and everything neutralized. We then move the negatively charged object near the terminal, and many of the negative charges run away to the foils, causing the foils to repel each other. But then, while still holding the charged object near the terminal, I touch the terminal with a finger. As soon as I do that, the foils come together. Then, when I remove my finger, there's no change in the foils. And lastly, when I remove the charged object, the foils repel each other and stay that way. They don't come back together. Let's look at what happened more slowly. When I touched the terminal with my finger, I added another path for the negative charges to take along my finger into the rest of my body. This is called grounding. There were still some negative charges on the terminal, but they didn't want to join the other ones on the foil because the negative charges on the foil repelled them. So for them, the repelling force of the negative charges on the charged object was balanced out by the repelling force of the negative charges on the foils. So they stayed put. But with this new path to take, they are repelled to my finger and away. My body's pretty big compared to this electroscope, so I can handle a small negative charge without making a significant difference to my overall charge balance. But now that they're gone, the electroscope's terminal is more positive than it was before, and that attracts some of the negative charges from the foils up to the terminal. Some escape to my finger and some remain. But now the foils no longer have extra negative charges, so the foils no longer repel each other. They come together again. Now with the negatively charged object nearby, we move the finger away. Nothing changes as a result. But now, when we move the charged object away, the foils repel each other. That's because the finger had removed some of the negative charges from the electroscope. There are no longer an even number of positive and negative charges like there were always before when we didn't use the finger. So everywhere on the electroscope, there are more positive charges than negative charges. It's no longer neutral. So now the foils are left positively charged. And since like charges repel, the foils repel each other. Another interesting thing is that since the electroscope is positively charged, when we move the negatively charged object close to the terminal, that forces negative charges from the terminal down to the foils, potentially balancing out the positive charges and causing the foils to come together instead of apart. The last interesting thing to show is what happens when I move a positively charged object near the terminal while the electroscope itself is negatively charged, with the foils repelling each other, like it is now. Note that when I rubbed the vinyl with the glass, while the vinyl became negatively charged, the glass became positively charged. If I move this positively charged glass near the terminal, that attracts some of the remaining negative charges from the foils up to the terminals, temporarily making the foils even more positively charged and repelling them even further apart. This was all a demonstration of charging an electroscope positively using my finger and a negatively charged object. A similar sequence of events happens if you charge it using a positively charged object instead, and then touch with my finger again. Just keep in mind, positive charged protons don't move around, only the negatively charged electrons do. In that case, the foils will be left with a negative charge. In summary, this video demonstrated how to charge an electroscope by induction, and in such a way that it stays charged even when we move the charged object away.
All right. So far we've been talking about how charges can move around in a very qualitative kind of way. So we know that positive charges attract negative charges repel each other. But now what we'd like to do is we actually like to talk about the way that we can calculate how strong a force is between charged objects. And so the way that we do that is to apply a law called Coulomb's law. Okay, so in the video that I'm going to post this afternoon, there's going to be a pretty detailed breakdown of this, but since you guys haven't seen that yet, I'll go ahead and present that here. So what Coulomb's law says is that the force between two charged objects is going to be equal to some constant K times the magnitude of these charges, Q1 and Q2, divided by R squared times R hat pointing from 1 to 2. Okay, now let's break down this equation even more. So Q1 and Q2 are charges which are measured in units of coulombs. Something that's kind of nice if you're the first person to come up with an idea, you can name the unit after yourself. So perhaps one day we'll be talking about things in units of woos. So these charges are measured in units of coulombs, which are given the SI abbreviation C. The R is going to be the distance between two charges, and this is going to be in meters. And so let's draw a drawing of this so we can get a better idea of the way that this behaves. So if I have a charge Q1 and a charge Q2, and there's some distance R between these. Is this too small in the back? Can you guys see this? I can make it a little bit bigger. Okay, that's good. So the force between these two charges, Q1 and Q2, say this is two electrons. I have an electron here and an electron here. The force between them is going to be the product of the charge of those two electrons times the constant K divided by R squared, the distance between them. Now, the other thing that you'll notice here is that this is a vector. So this is a force that points from one charge to another, and so there's an associated unit vector here. And this unit vector, by definition, points from the first charge to the second charge, okay? So when I look at this system that I have here, if I want to find the force that 1 acts on 2, what's the direction that this points? It points to the right, and conventionally we say this is the x direction. So we're going to say that this is going to be r hat 1, 2 is equal to x hat. Aha! So now, what if I wanted to reverse this? What if I want to say, I want to find the force that 2 acts on 1? What's the direction of that unit vector? It's going to go to negative x, right? It's your left, my right. Correct? Okay. So that should give you all of the pieces that you need in order to determine what the units of the constant k are. Go ahead and work with each other to try to figure that out. Okay, so let's go ahead and talk about this one. So, what's the name of the tool that we use in order to do this?
Dimensional analysis?
Yes, dimensional analysis. This is a very important tool that the TAs and the LA and the SI, all the designations the other people have, can tell you they use a lot in very advanced settings even, to determine whether or not their answer is correct. Because we know that if I have an equation and say I calculated momentum, and it says that momentum has units of energy, well, I know that that equation can't be correct because momentum doesn't have units of energy. And so in looking at equations like this and then breaking them down to their units, we can learn whether the equation is correct or not, or we can determine what the units are on something that we don't know if we assume that the equation's correct, right? You guys trusted me that I wrote the correct equation here, and I think the guys that know probably would have yelled at me if I had written it wrong in the first place. Okay. So to start with, let's look at what the units are of the rest of the terms in this equation. So what are the units of force? Kilogram meters per second squared. How do we know that's true? Yeah, we can take this one back with dimensional analysis too. We know F is equal to MA, right? M is in units of kilograms. A is in units of meters per second squared. Okay, so we know this is F. We have F on the left side of the equation, kilogram meter per second squared. And this is going to be equal to K, the constant we're trying to determine, times 2 charges. So we get C squared, right? C times C is C squared, divided by a distance squared, which is meters squared. Now, this equation algebraically isn't quite ideal because I have a K here that means kilograms, and I have a K here that I'm trying to solve for, but I'm sure you guys will forgive me for the choices of variables here. But what we'd like to do is we'd like to solve for K, okay? This K on the right side of the equation. And so to do that, what we're going to do is multiply both sides of the equation by m squared over c squared, right? Because that cancels this side, okay? And so when we do that, we get that K is going to be equal to a kilogram times a meter cubed per second squared times a Coulomb squared. Okay? And that should be answer choice C. Okay? And like I said, this is a really important process to be able to go through, doing just about anything that involves units. You can use this in engineering, you use this in medicine. I hope that you guys have seen at this point that this is a very powerful tool and one that you should keep in your tool belt. Okay, any questions? Come on, try to stump me. Any questions? No? Okay. It's the first time I did that during this class. The guys in my class will know that I do that pretty often. Okay. All right, let's move on to the next one. So we have two uniformly charged spheres that are firmly fastened to and electrically insulated from frictionless pucks on an air table. The charge on sphere 2 is 3 times the charge of sphere 1. Which force diagram correctly shows the magnitude and direction of the electrostatic force? Now we have our equation here for Coulomb's law. That's kind of enough to determine this, but I'll give you a hint that Newton's also going to be important here. So as you're talking to your neighbor, be thinking about some of the things that Newton told us last semester and how they might apply here. Okay? Okay. Go ahead, discuss. All right, so let's go ahead and talk about this one. So who thinks they have the answer exactly right and can explain it flawlessly to the amazement of all of the rest of the students in the class? I know somebody probably does. You don't have to be shy. We won't judge you. Maybe a little bit, but no, we won't. No? Okay, so there, yeah. Do you want to try?
Yeah, I think 5.
5, why 5?
5 because from Newton's third law, if the forces, if one exerts like a force on 2 should exert the same force on 1, but because they are like charges, they should be opposite in direction.
Right, perfect. Everybody get that? So Newton's, whoa, there's a chair there. That was almost dangerous. Okay, so Newton's third law says that for every action there's an equal and opposite reaction, right? So if I act a force on the wall is going to exert exactly the same force back on me. And so when we look at these two charges, charge 1 is going to exert a force on charge 2, and charge 2 is going to exert a force on charge 1, and they're going to be exactly equal and opposite. That's one way to explain this. Does anybody know the other way to explain it? Somebody new, somebody different. Yeah?
Well, if you look at the equation that you gave us, so force acting on 1 and 2, or the force of 1 acting on 2, and I don't know how to explain it.
No, you're on the right track. Keep going, keep going.
So if you set it up the other way, the force of 2 acting on 1, everything would be the same, just negative.
Right, right. That's perfect. Okay, so let me just reiterate what she just said. So this equation, as it's written here, reads the force that charge 1 acts on charge 2 is equal to kq1 q2 over r squared. The question is, what changes if I ask instead, what is the force that charge 2 acts on charge 1? That's going to be, this is going to be kq2 q1 over r squared times r hat to 1. Okay? Now when I look at this portion here, does that look the same as it did above? I mean, barring an interchange of the order that I'm multiplying things, which doesn't change anything, right? This is exactly the same as this. So the magnitudes are exactly the same. But what will change is the unit vector. So this points from charge 1 to charge 2. This points from charge 2 to charge 1. Okay? Is it clear?